Hello and welcome. Today is May 30th, 2024, and we're here today with Dr. Wendell Sander. Wendell, welcome.
Thank you.
We'd like to begin looking at your life, which has been full of amazing accomplishments, actually, especially in the electrical engineering field, with a look at your early life, your childhood, where you grew up, your parents, what did they do, that kind of thing. Can you tell us a bit about that?
Yeah, I grew up on a family farm in southeastern Iowa. It was a farm that had been in the family for multiple generations. At school, my first year of school was in a one-room country school with no electricity and no running water. And I went from there to the town school, which was had all 12 grades in one building. And we were two classes to a classroom at that point, so it got up to 10 kids in a class. And then, excuse me, in high school, there were about 100 students in the high school, and so my class was about 24. It was in a rural area of extreme southeast Iowa interestingly, around us were three other small high schools of about the same size. One of them about 5 miles away, there was a student, Jerry Junkins, who was a few years behind me in college, and he later became the chairman and CEO of Texas Instruments. So that was kind of interesting. And another little town about 10 miles away, there was a preacher who had a son while he was there, and the son was Bob Noyce. So we grew up in a neighborhood where actually there were a surprising number of interesting people came from. This is a typical agriculture community. And I went on and I graduated from high school in 1952, and then I went to Iowa State University in Ames, Iowa, and in electrical engineering, and got my electrical engineering degree in 1956. And from there, I went on to work for a company. It was actually Gilfillan Brothers, which is a rather old line company in California, because in the early days it made lots of radios. Before the World War II, it made radios and refrigerators and appliances and all kinds of things. I guess when World War II started, they came to Gilfillan and said, "We need you to make ground control approach radars." And they said, "Well, we don't want to do that. We want to make radios." And they said, "Well, you can either do it or we'll nationalize the company and then you'll do it." So one way or another, they went into the military business. And in '56, when I went there, they were doing ground controlled approach radars, and also they were doing a missile system, and I worked on a missile system there. So I was there, and I left after a couple of years to a startup that was doing some contract work for the FAA. And then in 1960, I went back to graduate school at Iowa State University and got my master's and doctorate there, graduating in 1963.
Wonderful. Can I just interrupt for a second?
Sure.
Yeah, because you've raised a lot of really interesting things.
Okay.
So Iowa State, of course, is where John Vincent Atanasov was.
Yes, that's correct.
Was based, and he was the winner of the famous legal case
Yes.
of Sperry Rand versus Honeywell, and as the inventor of the electronic
Yes.
computer. And so that's a very nice university there. Were people aware of Atanasov's reputation when you went there? Or?
No.
No.
No, that was they were not. He was fairly obscure there, because really his work had not gotten much notice there. I guess he did some. My understanding is he did some projects for some of the physics department and things like that, but it was pretty unnoticed.
Right. And now Bob Noyce went to Grinnell, I think.
Yes, he did.
Can you tell us a bit about that college?
Yes. Yes, Grinnell actually is a a religious school. His father was a preacher, and he was a preacher in the town of Denmark, which is close to where I grew up when he was born. And it wasn't long after that they moved to Grinnell, and his father became part of the school, since it was really a religious school of that religion. And so that's really why I think my Bob Noyce ended up going to Grinnell for his first 4 years. That was his hometown at that point. So
now, somehow Bob Noyce got hold of some very early transistors. I think they were point contact, but they might have been junction. I'm not 100% sure.
They probably were point contact, yeah.
Yeah. And now, since you're getting your PhD just around the time when transistors are sort of exploding on the scene, what did you make of what did you and others make of the transistor when it was first announced? And
well, it was pretty much obvious. It was pretty clear that this was a big breakthrough in electronics from what we could see. And it was interesting because of course the classes and laboratories had not yet evolved to transistors. We did have a few transistors in laboratories. They were germanium transistors, probably junction transistors, but they were germanium, and they were it had things like thermal runaway. I mean, they could leak enough to sort of bias themselves. But at the same time, one of our laboratories, we built a vacuum tube radio receiver that we used, was a project,
using transistors?
No, using vacuum tubes.
Oh,
it was a classical. And my lab partner happened to be a veteran, and he was working in town as a radio repairman.
Oh yes.
So we had an easy time with that.
Yeah. No.
But I remember he put his little finger on ground and went around to the taps and says, "Oh, we got voltage everywhere," because there, of course, around like 150 volt.
Oh my gosh!
On those things.
Yes.
But that was how he did it.
Yeah, that was one of the nice features of vacuum tubes.
Yeah.
We actually have the console from the UNIVAC 1, the maintenance console, and I think I counted 28 different voltages.
Yeah.
On the UNIVAC 1.
Yes,
yeah,
I believe that.
So yeah, and that's a vacuum tube machine, of course.
We used to buy batteries for the battery-operated portables in vacuum tubes, and those would have multiple voltages, and
yes,
they were quite challenging batteries.
The A and the B batteries.
Yeah, A and B, and
right. Yeah. So tell us about your dissertation a bit. Did that? What was that about?
My dissertation was interesting because it was kind of far afield. What I had done when I was at the startup, I was doing a mixed analog digital computer. They were trying to get flight path computations done, and so had worked with analog. I'd designed an analog to digital converter and done a few things like that, and so I was interested in for my dissertation, I was interested in coming up with a mathematical description of an A to D converter, and because really there was no way to do that very well. So I actually, and it was kind of interesting because I had a major professor who was pretty laid back, but he's a very sharp guy. But he was and so I saw him in the hall one day, and I mentioned, I think I'm going to do my dissertation on this topic. He said. We were there for maybe 5 minutes. He said, "Oh, that sounds pretty interesting." And so the next time he saw it was rough draft form. So, so this was really my own work. And what I did is I developed a theory of two-valued variables so that you could describe things with orthogonal polynomials and two-valued variables. And by doing that, it turned out you could, if your result was a two-valued result, of course the variables were that, but the result didn't have to be two-valued, which then allowed you to mathematically describe an A to D converter. But it also allowed you to describe Boolean results, so it was an alternative of Boolean algebra. And I had a few friends who took that up as their way to design logic after that. So that was my theory. And it was interesting because for my PhD they required 2 minors, and my minors were mathematics and statistics. Iowa State had a very strong statistics department, primarily because they developed a lot of hybrid seed corn hybridizing technologies, and that required very sophisticated analysis of the sites to be able to get statistical results that were meaningful when you're growing in fields you don't have any control over much.
That's fascinating.
So they had a very strong statistics, and so I made the statistics professor on my thing very happy, because I had inadvertently made a proof that there were certain conditions under which the orthogonal polynomials always converged. And I thought that was pretty good. Anyway, so my dissertation was totally off in a different area than I ever worked in before or after.
Right. Now, although the fact you did it on A to Ds is you did do some work with A to Ds later on, I think.
I did it.
Yeah.
I did it times.
And before as well.
Yes,
Yeah.
I did before, and I did after too.
Can you tell us a bit? I'm just looking at the Tasker Industries stint that you had there. I'm curious. Could you?
Yeah, that was the company that was a startup that was in did contracts for the FAA, and the FAA was trying to get some equipment for their sites that were automated, and actually I was doing a hybrid version of some of the computation, and there was another team, company, actually doing an all digital approach, which eventually won out, which is pretty typical of how things were going in those days.
Yeah. Now, was this part of the ILS?
No, it was. Well, it was. Yeah, it was. We were trying to. It was the ground approach. It was the approach patterns we were trying to track. So we were doing flight paths, tracing flight paths, approaching flight paths for trying to time management of the landing. I don't know what it became really considered, but I was doing computations of flight path analysis and timing.
Is this a radar-based technology?
Yeah. You were tracking. You were tracking with radar.
And it was just one radar dish.
Yeah, or there may have been more than one, but you were getting tracking information to try to control all this.
I don't know if you know.
This was in the 50s.
Yeah, well, I was just, it reminded me of the SAGE system. I don't know if you know that.
It was probably contemporary with.
Yeah, well, they had like height finder radars and azimuth radars, and well, that's very interesting. Yeah, and so you were there for maybe a year or two.
Just a couple of years, and then I went back to graduate school. Actually, I was still.
Right.
I still worked for them during graduate school. I I worked summers in there. I spent a summer in Atlantic City at NAFEC. They had the test facility for the FAA was in Atlantic City.
Oh.
So I spent a summer back there on my summer vacations.
Right.
So that was, and I did the usual things. I was a assistant teacher. One interesting student I had a student who was legally blind. He was so blind he had to use Braille. So I had a double E student who worked Braille.
Oh,
and
wow.
so when he did tests, he would do them in Braille, and then afterward I'd sit down with him and he'd tell me what he did. But one of the most interesting things was, in order to get a degree in electrical engineering there, you had to pass a drafting course. And of course, conventional drafting course is just not going to work. So the drafting department actually formulated a special course just for him, that he could show all the principles of drafting, even though he was blind.
Wow, that's nice.
Wasn't that something?
Yeah, that's really nice. They accommodated him.
Yeah, they accommodated him.
There's another famous programmer. I don't remember their name. I think they were on Johnny-Ac, but they also had severe vision problems and just extremely bright, but limited by their vision. Yeah. So you've got your PhD now. What's next?
Well, I went back to the same company for about 9 months. But then I got.
Sorry, this is Tasker?
Tasker, yeah.
Okay.
And then I got recruited. At school, I had one of the other students was Bill Smith, and he had gone to work for Rex Rice at Fairchild R&D Labs. Rex had this digital systems research department at the laboratory, and his background. I don't know if you're familiar with Rex Rice, but his background, he had been at IBM. He had actually become he started his life as a mechanical engineer doing stress analysis, and got involved in one of the really early Binac machines doing stress analysis on computers, and developed that. And then he went to work at IBM and worked there for a number of years and was a recruiter for them. And in one of the places he recruited was at Iowa State for PhD candidates. And so he was, when he went to Fairchild, they recruited him to Fairchild. When he went there, he was recruiting at Iowa State. So he took a couple of the graduate students I'd gone to school with to Fairchild. And so they got a hold of me and recruited me up to Fairchild. So, and that's when I went to Fairchild R&D Labs, which was
wonderful.
quite an experience.
A couple of quick questions. Does the name Cuthbert Hurd mean anything to you?
I know the name, but it doesn't.
Yeah,
I don't place it.
He was IBM's director of applied science, and he and Jim Birkenstock went out and got orders for the 701.
Okay.
IBM's first,
Yep.
large scale.
Those names I know.
Computer, yeah. And then, what was the other thing I was going to mention? Rex Rice was also in charge of the Symbol project,
yes.
right?
That was the project they did there, and that's what I was recruited to work on.
Okay, this is really interesting. You know why? We have the Symbol machine.
Yes, I know you do.
Here in the collection.
Yes.
So why don't you tell us, well, let's go in order, and so tell us when you started there.
Well, I started there, and I was in the Symbol group, but I didn't stay there long. But I was in the Symbol group, but I was there long enough because Rex was also one of the inventors of the dual inline package. And so we had dual inline packages, and I did some of the very first thermal analysis of the ceramic package for thermal characterization to determine.
Wonderful.
So I had to work on it real early. But I didn't work there long, so I didn't do much on the Symbol myself, but I knew the team well. And I actually went back to the team later to do the Iliac IV stuff.
Now, was the dual inline package developed for Symbol?
No, it was really developed for Burroughs. For both. I mean, he made the comment when he got there. What they showed him was the little flat pack with a bunch of flimsy leads on it. And he said that was pretty impractical on the state-of-the-art printed circuit boards. That was a nightmare.
Yes.
He wanted to do something different, and he worked with Burroughs. They were interested in coming up with a practical package that they could use automatic insertion on. So he worked with them, and actually, because he was a mechanical engineer, it helped because he was able to determine how you shape them, and the fact that the leads had a spring to them, and they were designed so that you could grab them and put them in these plots, and everything all worked. It was a fairly significant amount of mechanical design went into the dual inline package so that they could do automated assembly. So that was kind of his contribution to it. And
can you divide between Burroughs and Rex Rice?
Between those two, I was mostly Rex is the one who came up with the package, but Burroughs he just worked with Burroughs they were a counterpoise. The patent I think the patent actually was Rex and somebody else there. There's another engineer there were a couple other people at Fairchild that really did the package.
Right.
And they aimed it at the problem Burroughs presented them, and for the parts they wanted to buy.
Right.
And it was really first used on a IC logic technology that never really had too wide a usage. It was used on some of the early Burroughs machines and used on Symbol. It was they called it CTL, complementary transistor logic, and it was. But so they developed it for that, and then of course it just took off. once they got it, the package showed up, everybody wanted their parts in that package, and so it exploded then.
Yes. Well, that's wonderful. Can you comment on the Symbol machine? Like, what were the goals of the project?
The goals of it, Rex had the concept that software, there was just too much software definition. You needed to have more, that things would operate more efficiently if you put it in hardware. It would operate more rapidly. You could accomplish these objectives more efficiently and rapidly in hardware than you could in software. So, I mean, in other words, a special purpose machine was going to run faster than a general purpose machine for the same thing. So they aimed it at doing the they developed their own high-level programming language, and they implemented the language in hardware. The other thing was databases, because he felt that all computers ought to be variable field length. You shouldn't have to talk about how long things were. You could be able to handle an unlimited word length if you wanted to, bit length. The numbers should be variable, and it shouldn't be confined to these chops. And so everything was done in a streamed fashion, so that all the arithmetic was effectively independent of the size of the variables. And his search, he was always interested in all kinds of search algorithms for searching information. Of course, at that time, most of the information was fairly short information. It wasn't like webs, it wasn't like searching on the web, where you're looking for massive. It wasn't massive data analysis. It was more confined. But he was very interested in all those aspects. So the Symbol machine was an attempt to build a machine that was aimed. It had the variable field length, all the variable, even all of the variables were variable field length, so it was just a different way to do things.
And can you describe how you implemented the instructions, the software? Like what?
I'm not even that familiar with it.
How would they have done that? They didn't have ROMs. Maybe a diode. ROM.
It wasn't coded. You understand? It was logic.
Oh.
It was done in logic, not in code.
I see.
That was the whole point. You do everything in logic, and it goes faster.
So it's just regular
combinatorial.
Logic.
It was just combinatorial logic.
Yeah.
So you had massive amount of logic.
Okay.
And that's how it was done. So it was not, you didn't think in terms of any programming in it.
Did Symbol have any positive outcomes?
Well, there were a number of articles written about it, and so it made some in the literature. That was really all it did from positive. It's certainly things like, you can say the dual inline package was partially an outcome of the research and stuff like that. So there were a few outcomes. The packaging technology of the Symbol was done in a fashion very similar to the process element memories. There was the same physical structure was used for Symbol and the process element memories that you have out there for the Iliac.
Can you describe what you mean by that?
The connectors were cam connectors, so they dropped in and you turned cams to force the pins against, and that was done to guarantee you had reliability, because you were able to get enough pressure and wipe when you clammed those things that you guaranteed a result.
Yeah.
And and that again was Rex's mechanical engineering background. He knew what you had to do to make a very reliable contact, and he knew he was putting in these rows, which he had, I think, 400 contacts a board or something like that, and about 20 or 30 boards. He had thousands.
My gosh!
Huge numbers of contacts. They had to all work, and they did.
Wow.
He knew how to do that. Yeah.
That's incredible. And is it time to talk about the Iliac IV? Or
we can talk.
Do you have something in between?
Well, there's that was it's a longer process, and it's not just because what happened was I was off doing some work on large scale integration, and so I did some of the earliest gateway. I had a group doing the earliest gateway work there at Fairchild. So actually, even the first ones that came out, I forget, the 3100 or whatever it was, that was really developed in a group I had. So we were looking at all kinds of ways to do large-scale integration, because that was what do you do after the small parts to do big parts?
Are you
And
still
gate arrays were one structure we looked at.
Sorry, are you still using manual layout?
Well,
tools?
first we were. Actually, we built some where we actually used conventional PC board taping to create masks.
Okay,
yeah.
right.
So we went, but yeah, we didn't have really much in the way of computers yet. And so when the computers came in, of course, all that started changing a lot.
Right.
But so I did that group, and then it went off, and I was just doing some research, and I started working on memory chips. And so I looked, and I came up with a way to make a 256-bit chip in R&D labs. And so I built a 256-bit memory chip, the working memory chip in the lab, that was, the way it's structured was very fast. It was sort of based on the CTL process, which used AND gates for logic and stuff like that. But this was but I was able to make a very small memory cell because I used the epi space as resistors for the loads for the chip, and so you could just float them in space, and you could just drop in. You could make a very, very tiny bipolar cell that way. And H.T. Schwa, I showed, went over it with H.T. Schwa, and he saw that, and he did a little different, but he took that, and that's what made the 4100. So he took my design to the 4100. And matter of fact, I had also built a tester, because the first time they tested it, when I had built the first ones, the tester basically wrote all ones and then all zeros, and then read all ones and read all zeros. Well, a flip-flop passes that test. And so they made a few chips that were basically a flip-flop. All you're reading was one bit.
Yeah.
But anyway.
And
so,
this is a 256 by 1 bit part,
yeah, 256 by 1 bit.
Yeah.
Had this peculiar encoding on it because because the encoder, when you had to do inversions, took a longer time, and I was trying to make a really fast RAM. So we used this combinatorial coding to do that. So you just, anyway, so you get away with that without inversion on the chip. Anyway. And Schwab followed that too, because the 4100 had that kind of addressing on it. But anyway, so I built this tester, I hardwired a tester to go through and do a few other patterns like checkerboards and diagonals and things like that. They used that tester in production for I don't know how many years.
Oh.
They took it. And I'd put it on this board, and I'd put my name on it. So it was the Wendell Sander tester, and it got called that, and everybody in production called it that.
That's nice.
But,
so the 4100 did that become a big seller?
Well, it was pretty big. It really was the beginning of their static RAM business they did, which were the bipolar. It used the oxide isolated process stuff.
Did you have any competitors at the time? Was anyone else making?
Right, and at that time, no. For at least a number of years, we were the only ones making a 256 by 1. We had a couple of years there at least.
Yeah.
So we built the process element memories for Burroughs, and we actually also built a couple of replacement megabyte RAM units for IBM machines. There were boxes that you take put them in replace the boxes.
Now, I read in one of your interviews, is this the one that drew 12 kilowatts?
Oh, yeah. Oh, man. It had
5 volts at 600 amps or something?
Like that, yeah.
Yeah.
Yeah. Oh, yeah. It was tremendous amount of current. We had these huge copper bars because those chips drew a lot of power. They got hot.
It reminds me of the Cray 1 downstairs. We have that was an ECL machine. So
yes.
the minus 5 volt supply is 1200 amps.
Yes.
Yeah.
Yes. These bars were close enough together that you took off all jewelry when you worked around that thing.
Yeah. Very dangerous.
That was a welder ready to go.
That's right. Yeah. I'm very curious about the Iliac IV memory because we have one.
Yeah.
A PEM,
Yeah.
which I thought stood for processor element memory, but it's process element memory.
Oh,
is that right?
I don't remember.
No,
but yeah, it is process element.
I'm sure
That's what we called it.
I'm sure you're
process
correct. And tell us why that was so unique and how you got the contract for that.
Well, the problem was they needed a pretty fast memory, and magnetic systems weren't there yet, really. The only thing that came close was magnetic film memories. And there was I can't remember the gentleman's name, but there was one guy who was their memory expert at Burroughs, and he came and saw what we were doing in the bipolars, and he got in those things, and he was very interested in seeing it. So he was a big backer of it at Burroughs, but they were struggling to do the film memories with that performance or reliability they needed, to be very honest.
Right.
It was a tough one to do, and they were concerned that but they needed it. These things, they needed, I think it was 100 nanosecond access time, which at that time was screaming fast. So we could meet his speed requirements with these 4100s, and we showed it a few times, and that was enough. They ended up saying, okay, if you make them, they wrote the contract. And that was very significant because nobody had built a real seriously big computer with semiconductor memory. And there was a certain amount of question as to whether semiconductors were really reliable enough. I mean, Coors had the reputation of this really good reliability, and although they still did have error rates, but turned out that these semiconductor memories, that one was particularly hardy because it was a bipolar technology, which at the time was versus the MOS of the day was certainly a more rugged technology at that era.
Was it faster as well?
Well, it was faster. It was a lot faster,
Yeah.
but it also you got away from all. People were still fighting the little ghosts of the floating ions and all that stuff in MOS. It wasn't completely gone.
Yeah.
Even in that era. So it was really solid, and then it went in this case that Rex Rice had designed with all these super connectors on them were guaranteed to make connections, and the result was that the unit just never failed. Burroughs told us later that they were really reliable.
Oh, that's excellent.
They were very happy with the results.
And so the unit we have, which is on casters, by the way, which is great.
That's a whole process. That's a whole unit, though.
That's a 256K by? Is it? Do you remember? Or maybe.
I can't remember. Actually, I don't remember. I think it's 64, but I'm not sure.
Right, and how that must have been just an enormous contract for Fairchild.
Well, it wasn't. We just did the memories.
The chips.
The chips and memories. It was pretty good, but it wasn't a big home run thing. But it did put us. But it did put us into the position where, okay, now we'll go try making these big memories for the IBM world and see if we make those. Now, we did a couple of those. There was more struggle to that though, because we were putting these on these IBMs. Big IBM 60s. They were dual processors. I forget which one. I forget the number, but they were the big ones.
Yeah.
And they had so many cables. I mean, they had 4 of these massive buses, and I seem to remember there was like a couple of 100 coax. Were in the hundreds. You're talking about coax connections to the backplane of these, because you had two two peripheral buses and two processor buses you were dealing with, and all of them were 64 wide everything. I mean, it was just huge.
Wow. Now, Iliac IV had a lot of problems, of course, and
that
not related
was
to
over.
memory,
Right.
I don't think,
No,
right?
no.
Just it was behind budget and all,
Yeah.
I mean over budget and late and all that stuff. But did that help you get sales from other customers, being able to point to Iliac and say,
Well,
hey,
what it did, it from the viewpoint of the semiconductors, yes, because the semiconductor memory now was suddenly okay. So now the bipolar memory group did their thing, and they had a pretty good business in bipolar
Nice.
SRAMs.
By the way, I have a quick question. Is there a difference between Fairchild Semiconductor and Fairchild R&D?
Well, yes, yes. But R&D was really the R&D laboratory for Fairchild Semiconductor.
That's what I thought.
Yeah, is what it was.
Okay.
So generally, you didn't produce things in R&D.
I see.
It was not common.
Right.
There were a few exceptions. There were a few exotic semiconductors they made. They made some early light-emitting diode arrays for the military.
Wow.
That they used for. They did massive arrays of light-emitting diodes that they put on things that they used to put on stamped film for keeping track of the film, I guess, is what they did. I don't know. But anyway,
interesting.
At that time, it was because they were lead bonded, and every diode needed a lead bond on it, and so they had one lady who could do it. They had the skill set. Like one person with the skill set to make these things.
It's amazing how fragile things were in the early days.
Yeah.
And even today.
Yeah.
Still doesn't take much to disturb the system. Well, tell us a bit more about Fairchild. Just let's close out that chapter, if you like. And tell us what you did.
Okay, then. Well, it kind of is a segue to the next world, because we had done these big systems, and I was getting ready to leave because I was getting kind of burnt out and some stuff, and Jim Early was the head of the laboratory at this point, and Jim Early said, "Oh no, you can't. We want you to be head of the department for another project we have here," which was They had started doing a bipolar. They set up a memory research department to do a bipolar dynamic RAM, dynamic RAM done with bipolar technology.
Okay.
Because a couple of us had come up with some ideas for ways to try to do that. And there had been some proposals made by one of the guys at Bell Labs of possibly there was a way to do that. So they were built a project to do that. So I was made director, head of the department, which was kind of interesting because I was reporting directly to Jim Early, and who was the head of the laboratory, and they gave me a process line, process engineers, and design engineers, and all that, and so I designed this circuit, this bipolar DRAM circuit. And we built a 4K bipolar DRAM.
Wow. Now, what year is this?
This was, it would have been starting in about 74.
Okay.
It was actually, we started our project, I believe, before Moss Tech announced the first one, because what was interesting was we had already designed it with address multiplexing when they announced the address multiplexed RAM.
Mm-hmm.
Okay, so we were so the result was that actually our two chips were remarkably similar in terms of their design. They were a 1-bit, 4K 1-bit, and they had address multiplexed inputs that were looked almost the same.
Were these 16-pin dips?
Yes, 16-pin dips.
Okay.
Yeah, the objective was to get it in 16 pins. so I was working on this, and we got it done, and we had chips. So we had some working chips, and so one of the things I wanted to do is I wanted to put my chips in a real computer and see that they worked properly in a computing environment, make sure none more funny business in them, and so that was the beginning of the hobby computers in the mid '70s. So I went out and I saw an Apple I, and an Apple I used MOSFET DRAMs. That was the RAMs, and I knew that I could easily map mine into the same operating system they did, so I could replace those with my bipolar DRAMs.
By the way,
I bought one.
Sorry, did you have a type number for this bipolar DRAM?
93481, I believe. Is the
Oh,
number.
that's a long one. Okay.
And there's actually I have a rather poor copy of the data sheet. It was on data sheet form. I mean, it was brought to the point before they gave up on it that they were about to.
Oh, I see.
They
Okay.
What happened is they actually found a problem with making it in the process. There was a problem they'd missed, and they didn't have an easy solution for it. And so they just dropped the project rather than try to fight it more, because the MOS parts were just getting too hard to compete with. So but they had taken it to where they were starting to get ready to roll it into production. So
now the MOS, as you mentioned, can't compete on speed, so I guess it competes on power.
Well, it couldn't compete with these on speed.
Right.
These bipolars were definitely faster.
Yeah, with yours, yeah.
Yeah.
But it does compete on power, I suppose.
It's cost. Right? Well, power. Actually, they were about the same power.
Oh.
There wasn't really a power advantage. They were very similar. They were just really fast compared to the existing ones. When they were at 400 nanosecond access times, these things were 100 to 150.
Wow.
They were like 3 or 4 times faster. So there could have been a specialty market for it. We did talk to Cray about it, because they were obviously would fit that category. Anyway,
was that a capacitance issue?
No, it turned out there was a sneak. There was a sneak path in there that it literally was determined with a surround disturb test. I don't know if you know what a surround disturb is, but
no.
Well, in core memories, that was a common test, the surround disturb, because one of the things that would happen with cores is that if you did a whole bunch of reads and you had a row and you had a whole bunch of reads close to a bit, you could, because there was common current flow, you could disturb the bit and cause it to flip if you didn't hit it once in a while.
Right.
And this was enough that we could overcome the refresh. The refresh wouldn't catch it yet. Quite.
And what do you call that again, one more time?
Surround disturb.
Surround-disturb.
Surround disturb testing.
Testing.
Yes.
Excellent.
And that is a
wow.
old core memory test.
That's interesting.
And so that was how it was found.
And with this, this semiconductor.
But actually, my Apple I worked fine.
Oh yeah, sorry. Let's get back to that. So you put your own DRAMs in
the Apple I.
Did you replace the existing?
Yeah,
ones?
I replaced the existing ones. So they were gone. I had my own in there, but that also it had twice the memory in it, because I used more chips. So I just.
Did you just piggyback chips and move?
No, I had to make up a little kludgy floating board thing to fit down on the board pins, and I made it work, and it was pretty reliable. And so but at the time I just gotten remarried, and between us we had 4 teenage boys.
Oh, wow.
So I started writing games for it, recording games to it, obviously.
That's great.
So I wrote a Star Trek game, and of course I'd bought an Apple I.
Where did you learn programming, by the way?
Oh, I just
picked it up.
Just picked it up.
Yeah.
Didn't really, no formal training.
Okay.
But when you bought an Apple I, it was at that era. You had the 2 Steves and this other guy, and who drew the schematics. But so so I'd written this. So I'd gotten to know Steve because I'd call him up, and because when I first got it, the BASIC in the Apple I was still being written. I mean, one of the first version of BASIC I didn't yet have an input statement, for example. Yet it was just and every time you wanted an update, you called Steve and see if you could get an updated version of BASIC. And so that's
now you mentioned just really quickly, and I got to stop you. You mentioned you knew Steve, so tell us a bit about that.
Well,
how did that happen?
Well, that happens because I needed an upgrade to the BASIC. I knew I did because I knew the BASIC was old. So I called the phone number on the.
So you were getting to that,
and that got that got you Steve Jobs if you called that phone number. That's who answered.
Really?
Yes.
Wow.
Well,
I guess
wasn't
so.
anybody else.
There's
only just the two boys.
Yeah.
That's all there was. And so he answered the phone, and he'd say, "Yeah, we got another one," and I'd say, "Okay," and I'd go down to over to the house over there and pick it up, right? And
this is the one on Christ.
Cristo,
yeah.
So anyway, I got to know him, and I mentioned to him once that I'd written this Star Trek program for the Apple I, and he said he'd like to see it. So my son Brian and I went over and took it over there and showed it to him, and he thought it was pretty neat because it was running on a little bigger machine. I had more memory space. I could do it a little fancier than.
Oh yes.
So
right.
And then a little while later, he asked me if I could port it to the Apple II. They were doing the Apple II, and he wanted it ported. So in the early months of 1977, which is when the corporation of Apple started in January of '77. But by February or March, I was over there sitting at a prototype Apple II, porting my program to it. So I got to know Markula and Mike Markula and the Steves, and I thought this is pretty interesting. So I decided to make the switch and move over to Apple, and that was how I got into Apple.
Oh, wonderful. Now, from a technical point of view, were there things about the Apple I that you found clever,
well,
or was it just...
Actually, he is just very clever. First of all, Apple I was basically a TV typewriter with a processor on it. So conceptually, it's a very simple structure. I always say it's the last computer you could fully understand. And understand all of the software and everything. You could understand the whole world of Apple I.
Yeah.
Which is, because what had happened is Woz had been asked to design a TV typewriter for one of the local time-sharing services who were selling time-sharing service to people hobbyists who all over the place.
Oh, okay.
And so they wanted something.
Timeshare, maybe.
It wasn't timeshare. It was a different company in Mountain View.
Sorry.
I can't remember the name of it right now.
Yeah.
But they and I had used them too. I knew them. I knew who they were. But anyway, he had designed this TV typewriter. He says he designed it before he saw Lancaster's version of it, but he had used basically the same chipset that Signetics had made.
I see.
And he built this TV typewriter, and a TV typewriter was a thing with a key. You get a keyboard and hook to it, and then you'd have your TV set, and this thing would hook to a modem over here, and then your keystroke would send a serial stream to the computer and over a modem, and then you'd get back a serial stream which came up on your screen. And so what he did, he just took his TV typewriter and real quickly puts a 6502 in place of the modem and everything else, and just ran it in. You just run a serial stream in and get a serial stream out. That's all it is. Wow. So it's really simple. So that's its beauty, is its simplicity. I mean, he did. Now, apparently, even before they started shipping the Apple I, he was already designing the Apple II. And the Apple II, quite honest, is a marvel of efficient design. He is brilliant at certain things.
Well, this is where I'd love to pick your brain a bit about this. Are there any specific things that you found,
Well,
you can get very technical if you need to.
Well, yeah, the one that's very clear on that was his method of using the color channels on a TV set and getting them and being able to manage the color graphics, because he had a couple of techniques he used that took advantage of the characteristics of the set that obscure, in some cases not obvious characteristics, to get the color to work. And his designs tended to be very efficient. He worked very hard to do things that were. There's one example of that he did that I thought was pretty remarkable. Was, for example, when he tried to do a printer peripheral to run a printer, he had a code to run it, and what he did, you'd get his handshake back after the printer was ready for another character. It said handshake back, so you get this handshake signal back. Well, most people would run that back and go into the computer and stuff like that. What he did, he took the handshake back, and he would put it into an address line of the code. So now you had this code running to be able to run. So what would happen is you'd be running code and you get to a spot where it just branched to itself, and then when the handshake would come back, it had changed the address, and now it'd have a different whole set of code that he'd go to. So the new code, it would now follow the new code and drop through and loop. So he didn't need that. That was the handshake.
Wow.
Think about it. To me, that one struck me as being one of the more clever. That's an example of the kind of stuff he did.
And he's also good at software and hardware.
Well, yes,
seems,
he was good at
right?
software too.
That's pretty unusual.
Well, yeah, and what was, and the way he did software was a different world too, because you got to understand, he never used an assembler. I don't know if he ever used an assembler.
Wow.
And two things about it. He basically did the assembly manually, everything, and he could do hex in his head just so like nothing. I mean, he did hex like everybody else does their mental decimal arithmetic. He did hex, so he dealt with the branches without problems, and so he could just practically directly write linear code once he knew what he wanted to do.
Mm-hmm.
Then the other thing was that in the early days of the Apple I, in particular, he didn't have any he didn't have any memory system, any hard memory. So if you turn off the power, everything's gone.
Yep.
That means every time you want to start up again and turn the power on, you got to load everything by hand, in hex. So he could type hex faster than most people can type, period. So I saw him type hex, and he was blazing fast. So he had this property that he had completely comfortable typing several thousand bytes of hex.
Oh my gosh.
Because he would at the Homebrew Computer Club,
yeah,
he would sit down and type BASIC in, turn on the power, type his BASIC program in, and it's be able to demonstrate his computer.
Mm.
So he typed 2-3K of words there while they were getting started with the program.
Yeah, now one of the technologies that I want to talk about, because you had a big role in it, is the disk controller.
Oh, yeah.
And the IWN, which is the integrated Wendell machine.
Integrated WAS machine.
Or integrated WAS machine. Take your pick. Tell us about that.
Okay. Well, first of all, the encoding he used, you got to understand that he didn't have any background whatsoever in disk encoding. I don't even know if he knew how they did it. It didn't matter, because he just looked at what was coming out of the disk drive. He took a mechanical disk drive, understood what was coming out of it and what he put into it to do things, and he figured out his own encoding scheme. So he virtually totally invented the scheme. Now, it was a scheme, as a group coding they called it, which IBM had, they just sat around and dreamed up things like that and patented them. So they really had patents in a sense on a lot of that kind of stuff, but he just came up with this group code scheme, and it's just astonishing. He and Rod Holt was the analog guy, and he was really adept at analog design. So the two of them were a deadly pair on this, because Rod came up with this to simplify the works, and Woz tried to compensate to minimize how much stuff he needed from the drive, so he could keep that simpler. And but his encoding was this group code, and he was able to do it in the state machine and do all this and do all the things he had to do to get the thing to Cal, and took other shortcuts, and it was just a marvel of design. It was one of the really an exceptional. And you end up, we showed it at the computer fair the year later, and of course they'd bought these bare drives from Shugart.
Right.
And the Shugart guys themselves said later they just sent us the stuff that didn't work very good. So, so
and yet it still worked because of Woz's controller. Is
still
that
worked.
right?
He worked around. I probably helped him design a more rugged design.
You know, one of Seymour Cray's first machines he built using surplus transistors, and he put enough margin in there that they ran just fine.
Yeah.
And so that's really interesting. Wow.
So they had these things that ran, but he was able to figure out the way. And the state machine was really really nifty, and I actually went through and analyzed it totally, because I was trying to figure out a way to test these things. How do you test a disk drive now?
Yeah.
And I went through and I learned to understand the complete pattern of the state machine, which had to take different branches here and there. And it was just nothing but a 256 byte ROM and a register, and that was it. And but when I went through it and I realized that there was one path where was off by one bit in the timing. It was one count off in the timing. And so what was interesting was when they were starting production, they were concerned because they weren't getting a good enough error rate. They had to have a 1 in 10 to the 9th error rate. Well, let me back up. I was never known how good this thing was when it started. So the fact that it even could do 10 to the 9th was not obvious. I mean, you didn't find out till you started running these test programs.
Yeah.
So I look back and I think, man, but he really nailed it to be able to meet one. But he didn't. The ones they were testing were not passing. And I had this ROM where I'd corrected this one bit length. I said, here, try this. And so they stuck that in and it passed. So they all of a sudden, they couldn't. So they ended up giving me disk drive serial number 2.
Oh, nice.
Which I later sold for a lot of money.
Oh, yeah. And so one of the steps involved taking, was it 30 chips or so?
Oh, yeah, well, that was the thing.
And then getting it down.
That was the thing. You got it down to this board. The control board was like 7 or 8 chips.
Yeah.
And they weren't that expensive.
Well, one of them was a PAL, was it?
There were two. No, there was no PALs. It was all ROMs.
Oh, okay.
There was a state machine was a ROM.
Oh, yeah.
A 256 by 1 ROM.
Right.
Or 256 by 8 ROM. And they had a 256 by 8 ROM for the code too. And that was all. It was that and a couple of registers were all that was on there. And Rod had taken the analog board and cut it by more than half. He was down like 1/3 the number of chips. And so when we showed that at this computer show after we had it done, and they were demonstrating, doing loads and everything on it, and it was really a shock. I think it was really a shock to Shugart.
You know, I can still hear those drives in my sleep.
Yeah.
The unique startup sound. It's just classic. So I'm just curious. That must have been a big moneymaker for Apple, because they sold those for $4.95.
Oh,
right?
Look, there were a lot of things big money makers for
And
Apple.
there's no way
They
that
were
cost.
very profitable.
Yeah.
They were big. They were, and more importantly, the fact that they had a drive that was practical, even at $4.95, that was still a bargain, because you tried to buy the shoe guard equivalent for your
PC,
your for your well, not PCs, they weren't there yet.
Oh,
but
that's true.
I mean, it was the other players in the personal computer market,
Right.
the hobby market.
Yeah.
You try to buy the card was $200 or $300. It's like $300, and the drive was another $400 or $500. So these were bargains, and they were tiny.
That's right. And the typical configuration was to have two of them.
Yeah.
So there's $900. Well, almost $1,000 in drives right there. That's
And you got to realize the other big hit was when the first spreadsheet was put on on the Apple, and the reason it was put on the Apple is because they had a floppy drive.
Oh, is that right?
If you think about it,
The VisiCalc.
It wasn't feasible to do VisiCalc really without some kind of drive or
storage
system that worked.
Yeah.
And this was the only one that was really very practical for most people.
By the way, since we mentioned storage system, the Apple I did have a cassette storage, I think.
Even that was done. Even that was a very clever design, because basically, and that was another example of Woz's clever design stuff. Because what he did is you had one cycle of 1 kilohertz for a 1 and one cycle of 2 kilohertz for a 0. So the result was that so the length of the record was dependent on what the data contained was.
Is that a form of FSK, that encoding?
Well, I don't know what you'd call it, because it is kind of, but it's the only format I've really ever seen that if you record 4K bytes of it, the record length could be variable by 2 to 1, up to 2 to 1. And I don't know of any other storage coding system that does that.
Yeah.
To be very honest.
I know our IBM 1401 has a variable field length. The one that we have one running, by the way.
It does. Oh, it does. It has variable field length.
Yeah, downstairs.
Oh, well, maybe
we have two actually.
Maybe they do it. Maybe they were common. I don't know.
But they had a lot of core memory, and you could, I think, run out of memory. Obviously, theoretically. So.
But anyway, this was a. This wasn't variable content. This was the variable length of time to store a fixed amount of data.
Right. I see what you're saying. Yeah. And now, I always found, I used cassette storage maybe 2 or 3 times. And I found it very unreliable.
Well, this was hard to use.
It almost never worked.
It was hard to use.
Yeah.
What was interesting with the variable field length was I only really did it in recent years, but I realized that the way to check if you got a good load or not was to check the last 2 bytes, because if you ever got a bit error, if you ever read a bit wrong, then the length of the record was wrong, because the 1s were shorter. A 1 was half the length of time of a 0.
Right.
Okay, so by the time you read the length of time of the tape, if you dropped a bit, then that meant that the length of the record had to be wrong.
Yeah.
So you had to have compensating errors in order for it to come out right.
Wow.
So you could always look at the last bytes and see if they came out right, and if they didn't, then it wasn't a good load.
Now, was that the Kansas City standard that it used, or did that come later?
No, that was strictly Woz's.
His own thing.
It's unique.
Yeah.
It was used in the Apple II as well.
Okay. Yeah. Is there anything else you want to say about the Apple II, Apple I or Apple II? We didn't talk much about the II. How did you?
Okay. Well, I did a lot of the peripheral boards on the II.
Yeah, let's talk about that.
Basically, there was there's one of them is I did a print. The Woz had done a prototype printer card, and I did kind of cleaned it up for production and went through the firmware and made it was consistent with what we were doing. And there was a serial card that was just a super. It was just purely a serial in, serial out data thing. But then then I did a COM card. The interesting ones I did. Well, I did the RAM card actually, but that was kind of an interesting story because Bill Atkinson was doing. He was doing this other program, language program. He was trying to put a new language on, and I actually had done the ROM card too. I did, when they had AppleSoft Basic, they needed the ROM card to be able to switch between. That's the first solution they had was they sold it as a ROM card, and so I designed that and so what Bill was doing while he's developing this program on the Apple II was he was using EEPROMs and putting them into a ROM card so that he could when he was developing the program. But he was just continually burning ROMs to do that. That's a terrible way to do program
development. It's
a
very slow process.
It sure is. And so that's what he was doing. And I was looking at it, and that was Pascal. That's what he was putting in.
Oh, okay, yeah.
And so I think I'd like to play with Pascal, so I ought to, but I didn't want to buy all those ROMs. They were darned expensive, so I wasn't.
Pascal came on ROM?
Yeah, Pascal came on ROM initially.
Okay.
That's what he was developing it on.
I see.
Because that's what he was trying to do. Oh. So I said, well, I'm looking at it and said, well, gee, I can make a card that has just a DRAM and plug it in the card and pick up the how where you put the little dongle over to plug it in onto the main board, and I can do that and I can get that running. So I wire wrapped me up a card like that, so I could just load Pascal by moving it up onto my RAM card.
Oh wow!
So I took it in and I showed it to Bill, and he showed it to him and described what it was. He says, "Oh, I need that." He took the card and I never saw it again. So that was the prototype RAM card.
Neat. Now, was that similar to the Z80 soft card that Microsoft was?
Well, it wasn't, but it was just what it was is the RAM that replaced the onboard ROMs. So what ultimately was
for development.
You could put now a whole different program up in the RAM card.
Right.
So the ROM card did the same thing. It replaced the onboard ROMs.
Got it.
This was a RAM to replace the onboard ROMs.
So the RAM, that device was more of a development tool then?
Yeah.
Is that right?
Well,
yeah.
No. It went. Everybody got one.
Oh, really?
Eventually.
Oh,
yeah,
wow.
Everybody bought those.
Nice.
There were tons of them.
Yeah.
That was a huge one. So I did the RAM.
What was the most popular, the best-selling option card?
Probably the RAM card, without a doubt.
Okay.
Yeah, because you had to really have it, because that way you had both integer basic and AppleSoft Basic on your Apple II. And so
Did it interact with CPM at all?
Not really.
Needing
CPM
that extra.
CPM needed the Z80, and so that was why you had
true.
the Z80 cards.
Right. So
those, as external cards go, Z80s were pretty popular. Although even externally, Microsoft made RAM cards, and a lot of people made these RAM cards.
Yeah.
And
Quad RAM.
But all of them, interestingly, in order to pick up the address multiplex addressing, you always unplugged a real RAM chip and plugged this board into it to pick up the RAM addresses. And years later, I'll jump forward a few years after Apple. We did a company doing contracting. We were contracted by Apple to develop a RAM card with SRAMs instead, and that didn't need the dongle thing. And the purpose of that was, and the reason they asked us to do that is because they had gone to the Apple IIe's. And they had for the schools, they made a deal where you could do trade-ins of their old ones. And so they ended up with all these old Apple IIs that were not IIe's. So they wanted to do something with those. And so they wanted to ship them to third world countries.
Yeah.
Okay, and so, but they needed RAM cards in them to be able to do all the programs. So they had us design a whole new generation of RAM cards because the old RAM cards were too expensive to build because the DRAMs were hard to buy now.
Okay.
They'd gotten scarce and were real expensive. So
Right.
so we did another RAM card. Anyway, but the other peripheral cards that I worked on was the COM card I worked on. And the COM card, I ended up trying to design it in a way that it interacted directly with BASIC, so you didn't have to write any code to use the COM card. And it basically talked to a modem, which talked to the phone line. That was the purpose of a COM card.
Yeah.
And so I developed one that was easy to interact, but to do it, I only had 256 bytes of ROM to write a code in. That code was incredibly tight. And it was so tight that Andy Hertzfeld looked at it and said, when he came to work there, he said, I looked at the code, that was the tightest code he'd ever seen. And he said, one of the reasons I wanted to come to Apple, I wanted to come to some place where they write code like that.
Wow.
So I thought,
that's pretty nice.
that was a pretty nice compliment.
Yeah.
But anyhow, so that, but I wrote a couple of I wrote one really interesting program for using that card, because you could make the computer a remote computer. You could make the Apple II a remote computer. You could set it up for dial-in.
Okay.
So you could set up your Apple II and have it on your modem and dial into the modem and with the terminal and talk to your computer.
Wow.
Or you could have an Apple II at home and talk to your computer at work that way. So you could make two Apple IIs talk to each other, with each running their own. So I wrote a program called Telepong, and it was a Pong program that you could each person at the end of a phone line would load the same program, Telepong, and then you could launch it so that it would start. And what it would do, both programs would operate simultaneously. And you could now play Pong between the two, because the only thing it had to send over the phone lines was the paddle position when it got to the wall. So there was almost no transmission needed.
Right.
And the two computers actually operated independently on the two computers while they were playing the game. So it was a true interactive computing situation.
Yeah.
And later on, it was actually used, at least in one legal case, as early example of interactive computing, because it was a true interactive computer over a phone line.
That's amazing.
That's something.
And did Apple ever make its own modem cards?
No, modems, no.
Don't think so.
No.
Yeah. That was Hayes and all those other guys.
One of the guys, Marty Spurgell, he actually had a penny whistle modem that he sold. There was a kit.
Oh yeah.
He did. So.
Now was that a Lee Felsenstein design? The penny whistle?
Probably.
Maybe.
Very likely. Very
Yeah.
likely. They were good friends.
Yeah. Well.
But anyway, and I guess the last one that I designed of peripheral cards, I designed the graphics tablet, which is which was the one where you could draw on the tablet, and so I did that. That was all done. That was all done in the 78, 79 time frame.
Mm-hmm. Did you work with Rod Holt on that at all?
Yes, he helped me on drivers for that.
Because I interviewed him, and he was actually kind of annoyed that Apple didn't market it properly, and they kind of just let it,
Yeah.
They didn't think the market was big enough, so they didn't bother really.
Yeah.
But anyway, that's the way it goes.
Yeah. Did you had interviewed Rod?
I did, yes.
Oh man.
Yeah,
he was an interesting guy.
Oh yeah, lovely man.
I really liked working with him.
Yeah. Oh yeah. Yeah. Because he's both of you are just so accomplished and so smart. Well, Apple now. Is it time to talk about the Apple III?
Yeah.
Okay.
Okay. Let's. Basically, the beginnings are the reason the motivation for the Apple III is really interesting, because the problem they had was they were making the Apple II, And the FCC had in the games world, or where the home games, they had developed a standard that the what do they call it? I forget now the title.
Part 15.
Part 15.
Yeah.
They developed Part 15 for games.
Right.
And the standard they wrote, it was very tight, very difficult. And Rod in particular was concerned that it would just not be hard. It was going to be very difficult to meet that with a personal computer. So the aim of the Apple III was to develop a computer that could meet the gaming Part 15. That was one of its primary objectives. It was to be an upgrade too, but it was that was one of the big motivations of it. So that's why it ended up in this cast iron things with all these screws in it. It was just something else mechanically. It weighed a ton. And that was largely the result of a combination of industrial design and things. I mean, at that point, Jobs was involved in calling out the industrial design, but at that point, his heart was with the Lisa stuff, and
right.
It was the old. Anyway, we ended up with this box. It was a confined box to stick our electronics in.
Mm-hmm.
So we built it up, and then put probably too many bells and whistles in it, and it got too many parts, and it was tough to lay out and everything. So it was a difficult board, but one of the biggest problem it had was there's intermittent failures, and we traced them because we had 50 of these things sitting in a room burning, and it would have we'd have random failures. And what we traced it to was we had because it was a confined space, we'd stack boards. We had a board and we had a board stack, and the connectors to the board stack were some Molex connectors that were unreliable. Good old Rex Rice should have been there, but we needed them. They just didn't have enough wipe and pressure to meet the specification to work.
Are these the kind of like dip headers or SIP headers?
They're like with the pins. Yeah, they're like
pins that
the
stick
quarter
up.
square pins, and the connector slips on.
Right.
The connector was a Molex connector that it was a single pin, single wipe, and not enough pressure.
I used to make those when I worked in the summer. One summer, I made like hundreds of them. Anyway,
yeah.
Those Molex connectors.
Those things didn't have enough reliability for what we were doing.
Yeah, for sure.
Fortunately, this one guy found a connector that had been developed for the appliance industry that was the exact replacement fit, that had a really strong double wipe. They were a fork type thing, that metal fork that just slipped over. We replaced them, and that problems went away. I mean, that was just fixed it. And then nobody, it was too late, because by then people had a reputation. But Apple went ahead, and a year after they shipped the first Apple IIIs, they replaced every Apple III.
Oh, wow.
Every board was replaced.
Wow.
In fact, I had one time had one of the old boards, but at this point, I have no idea who has in existence a original Apple III board. I don't know of any.
Because they were taken out of circulation.
Because they were taken out of service and replaced.
Right.
And replaced, Apple used Apple IIIs for many years. Everybody in the company used Apple IIIs, and for years, and nobody ever complained about reliability problems.
Yeah, and one thing that I heard, and it's probably an urban legend, is that if it started working weird on you, you would pick it up 6 inches and drop it. Is that true?
You pick it up about an inch and drop it, absolutely, because it was a connector problem. All you had to do is just jar the connectors, and you were going to fix it.
So that's totally true.
Totally true.
Wow. Okay.
That absolutely worked.
And Apple actually issued a service.
I don't know
You're
that
not
they
sure
did.
about it.
I don't know, but
The word got
I know
around.
that it worked.
Yeah. Wow.
And that
Okay.
was because it had those connectors, and obviously that's exactly how you fix a connector problem. You just jar it, and it's gone.
That makes sense.
Yeah, it
Right.
worked.
How long a product life did the Apple III have? Do you remember?
I guess close to 10 years, I think.
Wow, because the Apple II was 17, I think I saw
well,
on
no,
Wikipedia.
the Apple III may have been just 7
So
or 8.
10?
See,
Oh,
Yeah, they were.
Well,
They were about 6 or 7.
With its variants, say 2E, 2 plus, 2C,
Yeah.
2CI, 2CX, all of those.
Yeah,
Well,
there were the Apple IIs were
Those
very
are,
long.
yeah, some of those are Macs, so I just threw that in there by accident.
Yeah, actually, there was a Max board for running the Apple II GS. I think there was.
Now, was the Apple III software compatible with Apple II?
Well, it wasn't really, and that was a problem too.
Okay.
Basically the marketing didn't. Marketing, let's face it, this was the beginning of the marketing of PCs, and they didn't really understand their marketplace very well yet. So there was sort of an assumption that, well, if you don't obsolete the old software, then nobody's going to use the new software, and that was a total mistake. Everybody's going to use all their old software. So the Apple II emulation mode was not supported properly, and there were some poor decisions made there, but that didn't help.
How about on the peripheral front?
There were never a lot of peripherals made for them.
Okay, but it used standard.
You could use the standard ones.
Parallel and serial.
Yeah.
By the way, I'm always curious about Apple Talk. Do you know the history of that or how that came about?
Well, not entirely. I know Rod worked on it, and there was
I wonder if the Apple III would have had Apple Talk.
Didn't have it built in native.
No networking.
It didn't really have.
Still too early. What
Yeah.
is that like? What year is that? 80, 1980?
Yeah, I think it was in the 80s.
Yeah.
That was the other thing. The Apple III went from concept to production in about 18 months.
That's amazing.
It was really fast.
That's really amazing.
And actually, the software for it was written really fast. That team did a very good job in terms of keeping a schedule. Software teams are notorious for not keeping schedules.
Yeah.
They did a remarkable job of keeping a schedule on that.
I think I've heard from many interviews I've done that the longest lead time thing is actually the injection molds.
Oh yes.
Those things have like a 6-month lead time or something. And so like everything else just stops until
Yeah, well that was
has to wait.
That was one of the early problems with the Apple II, and when I first got there, they were just going over from doing this early short-term tooling, which was very crude, to trying to get it clean. They finally decided to pay for the price of getting the proper molds formed so they could start running that stuff. It's getting the molds. Getting the machine to molds.
Another thing Rod told me was that the early Apples really weren't very compliant with Part 15.
Yeah. Well, no, they weren't. Oh, they were. Well, see, Part 15 didn't quite really.
It didn't exist yet, I don't think.
It didn't quite exist for computers.
Right.
And so, they were terrible. I mean, the Apple I was absolutely atrocious because I remember running my Apple I and being able to see it on my TV set. See the picture, the screen on my TV set.
That's impressive.
Didn't need a cable.
That's amazing. Neat. So, on the Apple III, and what is your fondest memory of that project?
Well, I think just getting it out and getting it going.
Yeah.
Of course, it was a bit frustrating with all the reliability issues, but in the long run, the other thing was seeing it be totally adopted at Apple for a number of years, 3 to 5 years. It was Apple IIs were gone, no Macs were there yet. It was just Apple III days.
Neat.
And that was
So the company at least
came
probably
to use it.
bought several thousand machines.
They bought a lot.
Yeah. Oh,
Anyway.
that's great.
So let's see, that pretty much is really the Apple days.
Okay.
I was there for about 5 years at that time. So in the early 80s, 82 or 83, I was part-time there for a while, and then the Houston brothers and Bob Lashley and I formed a company called the Engineering Department. And we did a lot of contract work for Apple.
Now, what kind of things did you build for them?
Well, this strange language card. We also did a contract. We did a contract for we were doing a project to put a card that ran the PC software in Apple II, and so we did the IC to do that could read the MFM's protocol of a standard IBM disk drive.
Right.
So we did that, and we worked with Apple to do what's called SWIM chip, which was a super Wozniak integrated machine.
Oh.
Or sometimes it was really commonly called the Sander Wozniak integrated.
Nice.
Because my son Brian was the one who did the implementation of it, because he had graduated from college, and so he came to work for us and there.
Okay.
And he and I worked together for many years, well, virtually all his career.
That's a really lovely part of this story that I want to capture. And didn't you show me a picture? I saw a picture of Brian when you were just a little kid, and you were.
Yeah, there's pictures around like that.
Yeah. So well, let's talk about that, because he's graduated and he's just joined you. This is a perfect time to bring him up. And what was I going to say? I think you were mentioning, weren't you hanging out with the two Steves?
Well,
with Brian.
We took Brian. Brian went with me when we took the demo over there. He was in high school.
Oh, okay.
But
and to think of him as a vice president later is really cool.
Anyway, he was a manager. He was anyway, he was a director there, but he. Basically, well, I keep saying it's just like the old family farm analogy. I mean, in the family farm, the way it worked was you brought the kids into the farm, and they farmed, and they worked for you for years. And then when the farmer got older, he retired, and then he went to work for the son who now had the farm, right? And so we did the same thing. Anyway. He worked for me there, so he and I then worked as a team a lot, and generally I tended to come up with these crazy ideas, and he was a really skilled IC implementer, and so he could make it work. So we did a lot of projects where I'd work on the architecting something, and he would do the silicon implementation. We did that at a number of startups in the days when you could do that.
So he learned VLSI design at
was,
college and stuff.
Yeah. Well, he didn't learn it in college. He learned it basically when we really learned it on this first chip we did, because we did this. What happened was we did we did this. He started doing this chip where we did MFM encoded disk controller, and then Apple decided they wanted to integrate that in with the IWM and have both types of formats they could run on the same disk controller chip. So Bob Bailey worked with Brian, and really Bob Bailey helped train him how to do that. Bob Bailey was the one who did the original IBM and went on, and the two of them did the SWIM chip. And
wow.
And that's why it was called the Sander.
Yes.
But yeah, that was that was the SWIM chip.
Okay.
And that ended up going in the Mac and everything. The SWIM was the one that went everywhere.
Yeah.
So.
And what was the processor in the Apple III, by the way?
It was a 6502.
Same.
But I extended the addressing by trapping out on some of the codes and doing some extended addressing.
Okay.
So you actually could do 24-bit addressing if you wanted.
Oh, wow. It's a big address space.
Yeah, that was not for execution, but that was only for data. You could fetch data in a wide application. It was a kind of a trick I was trying to do.
Yeah.
Anyway, but
any other cool products that you worked on?
Yeah, then later, Brian and I did this controller. Wolfgang Dirks was their guy who did who was their disk drive guru at Fairchild. And interestingly, his father was Gerhard Dirks, who you may have run across before.
No.
Gerhard Dirks was a fellow at IBM fellow who really enabled the disk drive technology. He had developed. What had happened is he was in Germany, and he had developed a disk drive technology there, a recorded disk drive technology, and IBM had done the same, and they were beginning to compete in their patent world, and so IBM just bought him, and he moved over to the United States, and he worked here at San Jose. He was in the San Jose facility as their IBM fellow, and he was sort of was the father of the technology to a large extent for disk drive technology.
Wow. Did you know some IBM engineers? Did you?
No, I didn't really, but well, I did meet Gerhard.
Oh yeah.
But Wolfgang was his son.
Yeah.
And Wolfgang was a disk drive guy at Apple.
Wow.
So anyway, Wolfgang was working there, and he wanted to get a hard drive that he interfaced directly to the 68,000 they were using. He wanted one to put on the processor bus for the internal drive instead of having it through any other scheme. He wanted right on the bus. And so he came to us, and we developed a controller for him. So we worked doing that. And then Brian went to work for him eventually and worked at Apple on disk drive controllers. And so that was another step. And let's see, the other things, the disposition of the engineering department was kind of interesting, because one of the projects they picked up on the way was this obscure one where there were some guys in Gilroy who were interested in shipping containers to ship produce from all over the world. And one of the problems with produce is that it takes time to ship it, and it spoils before it gets there. So they were looking at ways to extend the shipping life of produce. Okay, so they'd come up with some environments that would extend the life by maintaining the atmosphere in the shipping container. At certain levels, you could extend the life of the produce.
Right.
So what they needed was a controller to control that, and we ended up developing the controller for the shipping containers to extend the life.
Oh.
So ultimately, the engineering department was sold to them.
Oh, interesting.
How's that for an exit?
That's interesting, yeah. Kind of reminds me of bananas. Like, we get them in New York. There's a huge sort of central market for bananas. They come from South America, Latin America, and so on. They're mostly green.
Yes.
And they pipe in ethylene gas to ripen them.
To ripen them, yeah.
So, anyway, so we're still at, it's got a really interesting name now. The engineering department.
Yeah.
How did you come up with that name?
Well, we wanted to do contract engineering, so
yeah.
we just said, well, we'll be the engineering department if you want one.
Okay, how about one more engineering department product that you worked on, if you can think of one?
Oh, that really is about
too much.
Okay, that's about it for them.
We can move on.
Okay.
Yeah.
Then the engineering department had been sold, and I was visiting my wife's family in Texas, and I got this call from Andy Hertzfeld. And he called me and he said, we're got a new company startup situation, and we need a hardware group. So I said, well, Brian and I are available. So that was General
nice.
Magic.
Both of you got to go there. That's
so
nice.
we both went, and and also the guy who did the Apple IIe, Walt Brodner, also went with us. So the three of us went to General Magic to do their hardware, because they had all these software ideas, but they had to put it on a platform.
Right. So tell us about that, because it was a very compact system, right?
It's pretty compact, but for its
time.
Yeah, but I mean, it involved designing a couple of chips, including a system on chip type thing. And
oh wow! That's
because-
pretty early for that.
Yeah,
isn't
this was this was relatively early in the system on chip days.
Yeah.
It was one of the contract chips chip designs you could buy.
And then for just people watching this talk, General Magic, just tell us what they made.
Okay, General Magic. There's actually a documentary of a General Magic that exists, and the idea was they were going to come up with a way to have instant communications just on a platform, and you could do it. It would be the kind of thing you'd order your groceries, you'd order things for them, and but instant communications to people that you could write notes and things. And they were doing the whole ball of wax. They were going to do the hardware, the software, and even the communication interface structure to do it. So it was actually launched by Apple. It was a spin out of Apple. Mark Peratt and Andy Hertzfeld and Bill Atkinson spun out. So we're starting this at Apple, and Scully decided to spin it out, and so that was the spin out. And they added Sony became a part of it, Motorola and AT&T. They were all part. All of them were part of this venture. So that was, I mean, their board included the president of Apple, the president of just about president or vice president of every one of those corporations.
Wow.
I felt they had to have an antitrust attorney at every meeting.
Yeah. And if I recall, each one of those companies contributed a specific thing. Like AT&T did a cellular modem, I think.
Well, they were providing the infrastructure. I mean, you remember the internet didn't exist, so it was
okay.
like building the internet.
Okay, so it was a radio modem kind of thing?
It was yeah, that was the idea. It was going to use cellular.
Cellular.
Yeah.
Yeah.
At that-
And then what were the other ones you
Well,
mentioned?
Motorola, they're just
yeah.
hardware. They're just going to produce the hardware. So
Okay.
then they did. They built hardware and
And
sold it.
And it's like a tablet.
It was
like
a tablet.
Device,
it was like
right?
a pretty good sized tablet with a stylus and
And it's
all
got
that
little
stuff.
wings, little speakers on the.
I don't remember.
Yeah.
I actually have
It's got little
one.
ears on it.
Yeah.
Like little. Yeah.
Anyway, so
Yeah.
this was the subject. So they had three different really staffing things. There was a hardware staff, because we actually built the prototypes for the Sony and Motorola to build their products. They
Okay.
and both of them actually manufactured and sold products.
Wow.
This just went all the way.
So Sony was Asia and Motorola was North
Well,
America.
they
or
competed.
Whatever.
They were really
Oh, they
competition.
both competed in.
They could compete.
Yeah.
They were both sold in the U.S.
Okay.
So
Wow.
it was a really quite a project.
Yeah.
But it was very high profile, and they were able to, because of all those sources. I mean,
Yeah.
they were able to draw from all these places. So they got some very skilled people, obviously, out of this.
Do you remember what you and Brian worked on? Was
Yeah,
it
we
these,
worked on
these
the
chips. That
we
were,
worked on the hardware and the prototype hardware. We actually had to design the entire product itself, because we gave them a working. We provided the working schematics for how this thing was built,
Okay.
and all and any special chips that were needed.
right.
Were provided. All this design work was provided by us. Now, we didn't actually sell them the chips or anything. We just provided them a design.
Who did the mechanical design?
They did. They did the mechanicals.
Oh, Sony and
Sony and Motorola they had their own teams on working on all this stuff.
Right.
We were just providing the electronics,
the reference design.
the reference design.
Right.
We did a reference design. That's
Nice.
basically what we did, and they both built product from it.
Oh, I didn't know that. That's really interesting.
And Brian was the manager of the product team.
Oh, wow.
So he was the one who did that, and he had hired this new engineer, Tony Fidel.
Oh, yes.
So Tony came to work for him. He was a dynamic individual even at that. And Megan Smith was another one.
Oh, yeah.
One of the hires. She worked for him,
Wow.
and so that was. And then I worked for him too there, basically.
Did
And-
Apple profit in any way from, or
no.
benefit in any way from the,
Well,
the technology, maybe? Or?
Not really. None of that technology really got. I don't think any of that technology really sunk in anywhere, to be very honest. It was a working experience, so everybody got experience with that world.
Right,
but,
right.
But that was about it.
Were you there during the Newton years at all?
Well, yeah. Well, Newton. Yeah. I wasn't at Apple, but Newton. Yeah. Well, Newton was kind of weird because I mean, Apple had spun out this thing to get it going. Then they went and started their own project to compete with it. So I never quite understood.
It's had a long life. You know, it sort of started and stopped a few times, I think.
Yeah.
Anyway.
So,
okay.
So that was that was General Magic.
Yeah, General Magic.
So tons of stories about it.
How long were you? Well, maybe tell us one or two.
Well, like eBay started there.
Oh.
It was Omar Yamajar worked there as a programmer, and he had a working site under his desk, and his wife wanted to sell some stuff, so he formed up eBay and just started running it because this is a little side effort to make things happen, and it ended up growing into eBay.
Oh my gosh, that's fascinating. I remember reading the first thing he sold was a broken laser pointer, which is very eBay, you know. It's like,
yes.
It might be broken, you never know. Anyway, anything else you want to say about General Magic, like what the environment was like?
Oh, well, it was a very
high stress or mellow?
Well,
or?
it got pretty stressful as things didn't pan out. And the internet, they should have just jumped on the internet and drove it. But, well, as Brian pointed out a lot of times, this is one of those situations where it was an idea, but the technology wasn't ready for it.
It's just a bit
it didn't exist yet.
Too early, yeah.
It was too early. That was one of the advantages of Jobs, was he was really good at getting things the right thing at the right time. That was really important. So anyway, that was
neat.
That was really kind of General Magic.
I know. What year did you leave in General Magic?
Oh, probably about 96, something like that. I think. When I went, about the time I went to.
I'm just looking at your thing. So
I think it says there.
November '97, actually.
97,
so anyway, there we go.
Yeah, Brian was there quite late. They for some reason they hung on to the hardware side of it longer for, I don't know exactly what the deal was, but they kept looking to be able to sell some of the system on chip stuff they did. And
did they ever do a Rev 2 of the
No, they
system?
didn't, but I think he was working on what they were going to do.
Yeah. Right.
I know. He was a very skilled designer because he'd done so much. So he actually they did one chip after things, and he was the only chip designer left at the company, and so he was alone. So he did a full rev of the chip and released it and built it and everything else solo. And almost nobody does that because he's about the only person I ever worked with who could check his own work. and because invariably in semiconductor, you have to have somebody checking.
Absolutely.
Absolutely. Yeah. And he was able to do solo designs.
Wow.
I don't know how he did that.
Very careful.
I couldn't do that for sure.
Probably got some of your genetic influence there.
Well, that trait was not one of mine.
Okay, so ChipScale, that's your next venture.
Oh, well,
Do you want to tell us about
really
that?
was along the whole area. ChipScale was, it started because early on I invested in this company doing microwave diodes. And it's a very niche market. But
yes.
Anyway, long story short, along the way they developed this technique for packaging semiconductors, where what he did, he would make wafers, and then he would etch grooves in them, and then literally and from the back, and then he would put plastic on them. He'd spin the epoxy on it, cure the epoxy, and then he could just carve out finished chips.
Oh, wow.
It was all packaged. He was doing batch packaging.
That's interesting.
So it was interesting. So a few of us got fascinated by that, and so we ended up trying to do a company and make something out of it. And we really couldn't get anywhere, but it didn't really go anywhere. But it did. We did get a whole series of patents in ChipScale technology, which were then sold to a guy who was trying to collect patents and make money collecting patents. And
this is really interesting because several companies, as you know, have tried wafer scale integration, and Gene Amdahl is probably the most famous one with Trilogy systems. But I'm not sure if you're aware, but they've come up the company called Cerebrus.
Yes, there have
with
been
now
some that are begin making it go.
It's real now, wafer scale integration. So that was a long time coming, and they told me they spent $200,000 in 1 year on one specific thermal management problem that was just like a showstopper, and it was because they had 4 different materials to deal with, and they were all expanding at different rates.
Yes.
And as they did so, they would disconnect.
Yeah.
And you can imagine. So there were 2.6 trillion transistors on that.
Yeah.
On that wafer.
Yeah.
Hard to wrap your mind around that. But anyway, so that's good. You sold the company and got some
we
patents out
actually
of
got
it.
some patent income. That was the only time I ever got any.
By the way, speaking of patents, I noticed you have 115 patents.
Yes.
That's remarkable.
Yeah, what's interesting is if you look through them, you'll discover there are a lot of different topics.
I did, yes.
A lot of different
very
subjects.
Very diverse. Yeah. Yeah, you've done a lot of really interesting things.
Yeah, because my next one was another interesting one.
Okay, tell us about that. Tropian?
Tropian, yes.
Yeah.
And that was, I'd run across, in this microwave area, I ran across this guy who was doing trying to do digital RF stuff.
Oh, yeah.
And so I connected with him, and I'd done this work I'd done on the disk controller was a digital solution to a disk controller, which is unusual, digital phase lock loops and things like that, which not a lot of people have done a lot on. And so I was working on those, and we talked about things, and he decided to start a company. So he started this company, and what he was going to do, he was going to do there was one of the standards for cell phones that he was looking at doing what do they call it, a version of a modulator which separated the AM and the phase modulation. So you did a phase modulator, and then you did an amplitude modulator, and that created the signal.
Okay.
And he needed a phase modulator, and I had ideas for doing a digital phase modulator for RF at up around 2 gigahertz and 1 to 2 gigahertz. So
interesting.
So that's what we worked on. So Brian and I went there, and we started working on this phase modulator idea, and a third guy, I can't think of his name, came with us who was a really PhD in communication theory. He had taught at the University of Pennsylvania, and so the three of us who worked out these, I had this idea for doing the modulator, so we got this thing, we got it working. And so we built it. It never really went anywhere. At one point we got a new president who decided to do, he wanted to do cell phone design, because we were kind of making them for cell phones. So we actually got some kits and designed a couple of cell phones there too.
Right.
Brian was in charge of ended up in charge of the engineering there, designing cell phones. So he was doing that. I went off to another company and designed another version of that phase modulator that was really quite exotic, using vernier techniques for detecting phase shifts. It was really crazy. Anyway, that's one of the patents. It's probably the most exotic thing I ever worked on. But anyway,
Are you a ham radio operator? by
I
any
am
chance?
actually now too.
Thought you might be.
Yeah.
Because your facility with RF is unusual in a digital designer.
Well, I wasn't one then though. What's strange
Oh,
is
I see.
I
Okay.
wasn't. There's this whole story to that too.
Yeah, please tell us. Yeah.
Well, I was. I did Tropian. That was what we did at Tropian, and the next one, the Amalfi, was also a variation of this.
Yeah.
But I had actually had a ham radio license when I was in high school for about a year. I was a novice, and I never really followed it. But about last November, October, of just last year, where I live at the Forum, they have an emergency preparedness committee because I have about 400 residents in a senior facility and spread along a hill next to a park, and there's a lot of reasons for worrying about emergencies.
Right.
Anyway, as a part of that, they have a group of radio amateurs who coordinate with the Cupertino Emergency Services in Santa Clara County.
Aries.
Aries, absolutely.
Yeah.
So they said one of the people who in that there came up to me and says, "Look, we need more radio amateurs. So why don't you go take your test?" So last like October, November, I took the first test, the technician class.
Good
test,
for
right?
you. Yeah.
So I took that and I studied for about a day and passed it.
Yeah.
And I thought, well, that was pretty easy, and I need something to keep me busy. So I went ahead and took the next week and studied
Yeah.
and got my general and extra class.
Nice.
Both. So I got all three licenses.
That's great.
And then I decided, well, geez, I got those. If you're familiar with that, now I could do HF,
Yes.
right?
Yeah.
So I thought, well, I ought to get an HF set. So
Yeah.
I got me an HF set and just a simple antenna.
Yeah.
But I'm buried down in a apartment complex.
Me too.
Where you can't get anywhere.
I know. It's really
So-
being HOA is the problem. Yeah.
Yeah. So I decided, well, okay, then I better get me a decent antenna.
Yeah.
So I
It's
did
all
some
in the
research.
antenna.
I did some research and discovered that, well, probably the best shot for me is a mag loop antenna, right?
Yes.
And so,
Expensive, but very good.
well, I
Yeah.
decided, well, heck, if I'm going to do this, I'll just design and build one myself.
Right.
So that's exactly what I did.
Oh, you built one.
That's what I'm working on still. I'm just get it done.
Wow.
So I now have, I actually got the programs and did modeling. So I knew what they were supposed to be. So I got the modeling programs and ran modeling programs and modeled up exactly what I wanted to try. And so I built it up, and I just in the last week or so got it functioning. It needs to be cleaned up, but I got it functioning.
Wow.
And the techniques I'm using are working extremely well. I don't know if I can really talk to anybody, but as a mag loop antenna, my standing wave ratios are phenomenal.
Wow.
So I'm really pleased.
How's the reception? Have you picked up?
I
haven't tried it yet.
I haven't tried a lot.
Oh, okay,
I've tried some, but they do there's one of the CARES handshake deals where they do an HF at 80 meters, and I'm looking at that.
Oh yeah.
But I get SWRs below 1.1.
Wow.
Just because I came up with techniques for tuning the
That's basically
SWR.
perfect.
Yeah, that's basically perfect.
You don't need it better.
You don't need it any better than that.
Yeah.
Anyway.
Oh well, that's fun. Good for you.
So anyway, I now am an amateur. But anyway, so we got diverted at Tropian. I left Tropian and went to Amalfi, but basically did the same thing. And this was really design of digital phase modulators.
Okay.
For RF. And
what kind of end products would these have gone into?
Well, cell phones. There were certain cell phone types that potentially could use polar modulation, where you modulate the two.
Okay.
And this is what it was aimed at.
Did you reduce this to a chip?
Or, yeah.
Yeah.
Yeah,
Wow.
most places. Two different chips on this.
And did they do?
They haven't gone anywhere.
Oh, okay. I was wondering if they would succeed or. Yeah.
But
It's a tough, tough market.
But Brian, in early 2000s, Brian decided, Tony had gone off and starting the iPod, and Brian and Tony talked to each other a lot. They were friends. So Brian decided to go to work for Tony at Apple. So in early 2000s, he went to work at Apple. And I was at Amalfi, went to Amalfi and was there. And when that wasn't really going very far, I decided to join Brian at Apple. So I went to work in 2005, I went to work for Apple. Brian was in the iPod group,
Right.
and I went to work for him. And about that time, or shortly after, he became the director of iPod hardware. So he was in charge of the hardware for iPods.
Was that John Rubinstein's old?
Well, it was, but John had just about left about that time.
Okay, yeah.
That was right about when he left.
Right.
And Tony took over all that.
Okay.
And about that time I came there, and then Brian was already there, and he took over the group, the design group. And I worked for him for several years. So
Love that.
One of the things, one of the public things that I did there was if you remember the earbuds they had a volume control on the earbuds.
Yes.
And I was largely responsible for the volume control design.
Neat.
It wasn't trivial because, I mean, the wires coming out of the earbuds were you had two stereo audio lines, you had a microphone line and ground. That's all you had. So the only way you had to run a signal from the button up to there, and what do you put it on? And so what we concluded was we put ultrasonic pulses on the microphone line. So we literally made a little ultrasonic generator in the buttons that sent it up the microphone line to go to
my gosh.
To go into the computer or into the iPod, and then put a detector in the iPod. And
That's incredible.
So it was kind of
that little inline thing that you hit with your thumb.
Yeah, it has
that's
a
what
little
you're,
chip in it.
That's what you're
tiny
talking
chip.
about.
Yeah.
Wow. I never realized it was so complicated.
Yeah, that's what they had to do. You had to do it
Wow.
with ultrasonic pulses.
That's fascinating.
And so that's what that was. And it was interesting because see, you had to have a receiver on it up there. And actually, we did that. It was remarkable. We worked with TI, it was a little group at TI, and Brian said, we ought to try to do this, and several of us got together, worked out a strategy, and I worked with them, and we got it working. And we did that in like 6 months. We had products using that.
Wow.
And then it was like one Christmas, and by the next Christmas, we had those in products. It was really amazing.
And those were made in the tens of millions.
Oh,
probably,
yeah.
right?
Well,
Maybe more.
In particular, in the ones in the host, the iPod host, those chips also had to be in every Mac.
Ah, right.
Because those earbuds worked in everything. Everything they worked in had to have a chip in it.
Yeah.
So I designed. That was my high volume design chip.
You know, I always remember, like, when you used to plug in a plug into a jack, right? It was a mechanical break before make kind of thing. And now it's just like, I don't know what's going on. There's a microprocessor analyzing this input, right? And is it an input? Is it an output? Is it, it's quite remarkable what they can do now with that one jack.
Not only that, but it doesn't matter which way you turn it.
Oh, there's that too, yeah.
That's
USB-C.
Yeah,
very nice.
I think the first one was the Lightning, was before the USB-C.
Oh yes, that's also nice.
The Lightning was where that started.
Yeah.
Because I got some patents on that too.
Oh,
some
really?
of my patents are those connectors.
Well, did you once you left Apple, did you finally retire, or?
Yes. Well.
Are you still working?
No, actually, you see, I went to work there in 2005, and I was 70 years old.
Okay.
So I was probably the oldest hire ever. But I retired, and I became a DEST, which is a Distinguished Engineer Scientist.
Right.
Anyway, when I retired, I was 75. So, but my wife had Parkinson's disease and macular degeneration. She was not well. So I was a caregiver for 7 years.
Oh.
So she passed away about 3 years ago. And that's when I moved from Morgan Hill to the Forum in Cupertino.
Yes, right.
So that's where I'm at now.
Oh, good. Well, anything else you want to say before we sign off?
I think that's probably pretty good.
Okay.
I'm surprised I talk so much.
You've been wonderfully forthcoming, and thank you so much for taking the time to stop by today and telling us the amazing story of Wendell Sander. That was really cool to hear your adventures.
That's my adventures.
Thank you, Wendell.
You're welcome.